Bienvenue au séminaire en informatique cognitive ici à Montréal, à l'UQAM. Je suis enchanté d'accueillir Ellie PAVLICK, qui est professeur d'informatique à l'Université Brown. Elle se concentre sur la paraphrase et la sémantique lexicale. Ses recherches portent sur les approches d'inspiration cognitive et l'acquisition du langage, en se concentrant sur l'apprentissage ancré du langage et sur l'émergence de structures ou de l'absence dans les modèles de langage neuronal. Elle dirige le laboratoire de compréhension et de représentation du langage qui s'appelle LUNAR, qui collabore avec les laboratoires de robotique ainsi qu'informatique visuelle dans l'esprit de l'ancrage et avec le département des sciences cognitives, linguistiques et psychologiques à l'Université Brown. Son titre a changé, mais c'est quasiment quelque chose. L'apprentissage linguistique et les mécanismes de raisonnement dans les modèles LLM. So the title of Ellie's talk has changed from understanding to understanding linguistic and reasoning mechanisms in LLMs. She's at Brown in computer science with a lot of links with robotics and with psychology. That I pass the gavel, which I mentioned is missing in the United States, but we still have gavels here, to Ellie PAVLICK. Well,
great, thank you so much. Yeah, it's great to be here. As Sivan said, I changed the title slightly, well, a lot. So I kind of generally pitch symbols of grounding large language models. This, I think, is kind of a subset of that. So I wanted to focus on some very new work, like 3 actually all unpublished papers by one of my students that I've been excited about. So I was excited about to talk to this audience about. It's more on the symbols side than the grounding side, but I think I sent along some of the papers that deal with some of the grounding work I've done. So if in Q&A people want to talk about grounding and those questions, I'm also happy to talk about that, plus the links between what I talk about in this talk and that work. So kind of the way I've been thinking about this work, or situating a lot of the questions we're working on, is in this ongoing debate that's been going on for a while about the kind of role of neural networks versus symbolic architectures for kind of explaining human level cognition and human cognition. And so it's typically viewed as this kind of two-sided thing, where there's, on the one hand, there's kind of the big neural network explains everything and you don't need to appeal to intermediate symbols. And so you can think of kind of the connectionism debates of the 1980s, which still have flavors that are around today. This is where people say, like, we have language models, these large neural network language models, they're doing so good at language. Clearly, you don't need to appeal to these more abstract concepts like grammars and symbols in order to explain that behavior. And then on the other side, there's, older work like Paul Smolensky's work, newer work on neurosymbolic architectures that say, no, like the kind of human cognition really requires this certain types of modularity and these different types of components that are functionally specialized and they interact in different ways. And that's what we need to really explain the full power and generalization and compositionality and reasoning structure of humans. And so what's been very exciting for me over the past couple of years, and really especially just in the past maybe 18 months, of looking at how large language models work, is this kind of pushing back on this assumption about that, like, the left side of this picture actually exists. So when we look at this we have this kind of cartoon of what a neural network is, which is just, we have all of these identical and nondescript nodes and they're all connected to everyone else. And there's no real interesting internal structure here. And so that's put up as kind of a point of contrast for these traditional models of cognition. But in fact, the kind of work that we've been seeing when people start trying to dig in and understand what's happening under the hood is that there's all kinds of mechanisms that emerge within these models that look a lot like much more traditional computing components. So there are pieces of the network that seem to be acting like these kind of content independent registers with reads and writes to them, or there's other places that seem to have these kinds of mutable like knowledge bases where you can update the value associated with a key and get kind of downstream effects of that. And so these things kind of looking at together makes the neural network look much more like a neural Turing machine or some kind of architecture like that than what we kind of traditionally assume when we look at things like large language models. And what's really interesting about it is how much of this structure comes as a result of training. So it's not necessarily built into the model, but it's something that we get after we've trained the model quite a bit. So I want to talk about, like I said, three recent papers. This is really just showing off work by my student, Jack, who's one of my PhD students and is awesome, as well as a undergraduate here, Chinan Yu, who's been working on some of these projects as well. So this has been work where we've been trying to understand whether these big language models actually exhibit the kind of internal structure that looks more like a traditional symbolic or at least neurosymbolic kind of model. And then that's maybe how it's succeeding in doing these really impressive, having these very impressive, seemingly complex behaviors. So like I said, this is all like very recent and unpublished work, but I've been excited about the kind of findings, and so I'm interested in hearing feedback from the audience. I wanted to start before going into the details of our specific projects with this kind of bigger picture of kind of, like I said, the kind of mental model of what a language model is, because this is something that has changed for me over the past couple, say the past year, as we've been working on this kind of stuff. And so I don't know if perhaps there are people in the audience who already have this working mental model of language models, but I did not. So I find it useful to talk about. And this is helpful because, like I said, I think when we look at something like GPT-4, one of these language models, we picture something like this type of a cartoon where it's this big black box that's mapping inputs to outputs, when actually my new mental model is that it looks much more like a traditional, like a neural Turing machine or some kind of more traditional computing architecture. So kind of the traditional way I think people have thought about, or I shouldn't say, the way people have tended to think about neural networks, especially these transformer models, which is what underlies all these large language models, is as a contrast to something like the recurrent neural network. So in a recurrent neural network, which is how we have, it's kind of the default neural network for looking at language, we process tokens from left to right, and we have this kind of dependency structure where the representation of the current word depends on the representation of the previous word, which itself depends on the representation of the word before that, right? So in this kind of model, if we're performing computations that are complex computations that unfold over time, that computation happens left to right, right? So we're going to kind of think of it as we incrementally get inputs over time, and we make updates to our state as the result of those new inputs, and we can carry out computations that way. And then we can have more and more layers to our network, which can allow us to have maybe more abstract representations of each time step. But the fundamental computation is really happening left to right. So we contrast this with a transformer. So the transformer model, if people are not familiar with the transformer model, I know this is mixed backgrounds. Unlike the RNN, which had these kind of built-in structure that was meant to model, language that takes place, again, like left to right over time. For the transformer, there's like no inherent structure like that. Every word can look at every other word, right? So there's very little kind of built-in organization to how this information is allowed to flow through the model. But with this change in transformers, we actually get a change in these two assumptions that I said kind of held for neural networks that help me, I think, help think about how the transformer might carry out these more complex cognitive computations. So a transformer looks something like this. We have these different blocks. So we have many layer transformers, and we get words as input that are going left to right. And each of these blocks has two pieces, an attention mechanism and a feed-forward network. So I'll talk about those, kind of why we care about each of those in a moment. So the first thing is the attention. The attention mechanism is really the like workhorse of the transformer. That's the the thing that makes a transformer. And the point of attention is that when I'm deciding how to represent a given word, the model is allowed to look at any of the other words in order to decide to do that. So perhaps we would have some sentences like cats like to drink, and I'm trying to predict milk. And if these dark arrows are showing where the attention is focusing, so maybe this orange, you guys probably can't see my cursor, but this orange thing that says cats drink is attending to, quote unquote, the word cats and the word drink. So we typically, so the thing that I have been, I like to emphasize is an interpretation of this kind of mechanism is what it really is this memory read write type of mechanism. Again, very similar to what we would have seen in like a neural Turing machine. So we have something like at this first layer, we have these discrete registers, one for cats, one for like, one for two, one for drink. And then at the next layer, what this attention mechanism allows this second to last register to do is read from the cats and the drink register and write to itself. And so we can think of this as having this read-write mechanism, which carries out over time, or which carries out across layers, where at each stage we're reading from the previous layer and then we're writing to ourselves. And all of these registers will write to themselves in parallel. Right? So what some of the earlier work has shown is that the way that this happens can be quite content independent. So where we typically think of neural networks as being these squishy association machines, we actually find that a lot of this attention can learn to read and write in a way that is quite independent of what is actually in that register. So for example, it can carry out a copy operation, just copy the word that's in the second register to the word that's in the third register, regardless of what word is in the second register. So that's a kind of like symbolic primitive that we would typically have in a traditional computer that we haven't considered being the type of thing we have in neural networks. And then the second piece of these transformers is not the attention, but this feed-forward mechanism. What the feed-forward mechanism can do is it can basically pull in extra stuff that wasn't there in the original registers. So this is where it gets to be much more neural networky, right? This is a kind of neurosymbolic part. If the attention is carrying out something that looks more symbolic, it's not perfect, but it can do that. The feed-forward net can start bringing in things based on loose associations from memory, right? So maybe when it sees the word cat, it can decide to basically add into the register information about milk and about meowing and about tails and whatever else it might want to do. And so these things kind of work together to allow this pretty powerful back and forth between carrying out some kind of symbolic like computations by reading and writing to registers and pulling in associative information from training memory. So the kind of upshots of this, and thinking about just how we think about computation happening in transformer, is first that we really want to think about time as going from bottom to top within the transformer. So if I have a complicated computation, we should not see it unfold left to right. Actually, all of the left to right dimension is really just a set of independent registers, right? But the time dimension is going to be happening top to bottom. So we should see these computations unfold from the bottom to the top, with more complex computations needing to take longer in order to happen because they're going to require more memories, reads and writes as they go up. And it also means that this register content can really be somewhat arbitrary. It makes them much more powerful. So even though we, at the initial onset, we've put the words cats like to drink in our registers, now that we have the feed-forward networks and we have these reads and writes going on, they can actually be quite arbitrary. So a lot of the work we've been trying to do is figure out like what's in these registers, what are the computations that are happening over them in order to carry out these more complex kinds of tasks. A third point I want to make, just because I'll make use of it throughout some of the studies we're doing, is that it's possible to basically have print statements as you go up the transformer to figure out what the intermediate computations are showing up to date. So there's really cool work by Mor Giva, who is a professor in Israel, but during her postdoc and PhD work, where she's been looking at trying to analyze transformers, and she has nice insights about why you can basically ask at any given layer for the model to predict the next word in the sentence. And this basically gives you insight into what the model's like thinking at this time. Sorry to anthropomorphize, but like if you're imagining a computation that's taking place over layers, you can say, when I'm halfway through this computation, what is the current content of like the model's registers? What is it thinking, right? So this is what we refer to as the residual stream. It's basically the ranked lists of words that the model is trying to predict that come next. But we can look at the residual stream at any point in this computation. We don't have to wait until the end in order to check it. So we might at the beginning have some kind of random stuff. The model hasn't really done any real processing of the input yet. And so it just has to guess based on the most likely words in English overall. So it might be guessing the, of, etc. After a bit of processing, as we go further up, it might have figured out something about the word drink, filter it down to a set of candidate things that might follow drink, but it's not very cat specific. As you get further up, it might start to get more cat specific. And by the end, it gets to the point of. Okay, so that's kind of like my, I guess, broader scene setting for the work we're doing, is that we want to be thinking about attention heads as carrying out these reads and writes across layers, and the tokens that we're looking at as being these arbitrary registers that can contain arbitrary content. We want to think about the feed-forward networks as being able to bring in new information from training, and that's where we really get that ability of language models to do things like associations. And then at each layer, we have this ability to get these kinds of print statements to say what is the computation that's happening over time. Okay, so from that, I want to jump into these three different papers we've been working on. And so the kind of first one, we'll be looking at the role of these feed-forward networks and how they work at kind of retrieving information from memory in a way that's modular and transferable. And the second one is like a shorter but a direct follow-up on that first one, looking at how the model decides whether to make use of this feed-forward network retrieval mechanism versus reasoning about what it already has in its registers. And then the third one is kind of zooming back out and just saying, when we figure out a particular mechanism or an algorithm that the language model is using for one task, does that tell us anything about how it'll behave on a different task? All right, so I'll talk this first one. Okay, so in this first paper, we're looking at a very simple kind of a problem, which is asking the model a question like, what is capital of Poland? And the model responds with, the capital of Poland is Warsaw. This is in like language model, world, we call this first part the prompt. That's something we input into the model. In this case, it's the question, what is the capital of Poland? And then the model responds, this part highlighted in green, it's saying the capital of Poland is Warsaw. This is GPT-3, I think, when we were doing this, when I made these slides. We're using a very simple, what we call an in-context learning setting, which is we're going to give it an example before the question we want it to answer. So here you can see, what is the capital of France? It says Paris. And then what is the capital of Poland? And it responds Warsaw. In this case, and something we will exploit later, but in this case, you can see it doesn't really need the in-context example in order to know what the task is. Like the question itself should be enough for it to say Warsaw. And as shown in this example, that models reliably do know that it's Warsaw. But what the in-context example tells the model in this case is to just respond with a single word, right? So rather than saying the capital of Poland is Warsaw, it's going to match what it's seen before and produce just the answer Warsaw. Okay, so what we're interested in here is, again, this kind of question about whether the neural network is really a connectionist associative machine in the traditional sense, or if it's doing something more sophisticated, something that looks more like a cognitive architecture. And so in possibility one, we would say that the way that the model solves this task, the way that it decides to say Warsaw, is by learning some big joint probability distribution that says, what's the probability of Warsaw, given all the other words that I've seen, and all the phrases and all the combinations of words in the context. And on a very literal level, like, we know that this is what neural networks do. Like, we know that this is a description of how the model arrives at the answer Warsaw. But if we think about kind of what is a useful level of description for describing what the models do. There's a second possibility where we say something like, based on this first input, the model infers some function, which it says there is a function that takes France to Paris. And now I'm being asked to apply that function to Poland. And so then that's how it gets Warsaw. So there's this much more abstracted level where it's looking kind of by analogy across from the in context example, and it's applying it to the new argument, which is Poland in this case. So we're interested in whether there's evidence of this latter thing happening. So we're going to look particularly, like I said, at the feed-forward network, because this is, I will say, when we started the project, we didn't know to look at the feed-forward network, but after a bit of analysis, we found that this is where the computation seems to be handled. And it's consistent, and part of the reason why I told that story I told before, where the feed-forward network really is responsible for pulling in information that's not in context, right? So here the word Warsaw is not available in the context. That's something the model needs to kind of retrieve from longer term memory, right? And so the way these feed-forward networks work is basically they're making updates to these registers. So here XI is the content of the register. We're going to run it through a feed-forward neural network, and it's going to produce this, what I'm showing as the red vector here, we're calling it O, this output, which gets added, and then that becomes the content of at this position at the next layer. So it's really it's just this single vector that's getting added to update the content of the register, this OI vector. And we find that a lot of the work is happening in this OI update to get from Poland to Warsaw. And so that's what we're going to be looking at here. But it's a very simple, just linear update, and that's just the way that the transformer is designed. So what we're going to do here is the first thing we're going to do is we're going to look at those print statements that I mentioned before. So what we can do is we can say at every layer in the transformer, what do you think the next, like, what do you think goes in the blank here? And you can see, and what we're looking at here is just the rank of the correct answer. So higher means that at 1, it means that Warsaw is at the top of the list. 0 means it's very far down the list. And you can see some very distinct phases that happen over the course as we look from the bottom layer to the top layer here. So in the earliest layers, you see that Warsaw isn't even in the running. This is just showing the top token at each layer, and you can see it's kind of just noise garbage. It's just saying A in parentheses. We're calling this kind of preparation grokking. I can, again, talk offline, but I think what's happening is a lot of attention moving things around, but the model hasn't really figured out what it's trying to do yet. Then you see an interesting point about just over halfway through the network, where the model suddenly spikes in the probability of the argument. So in this case, the word Poland shoots very close to the top of the list. And so this is, if we think about this kind of function interpretation, it's the argument to the function that becomes the top prediction at this point. And then very abruptly, we see that Warsaw becomes the top prediction, and then it remains the top prediction for the remainder of the layers. And so what we think happens here based on this is that if this function is being applied, it's being applied here at layer 19. Prior to that, the model got the argument in place, and then it applies the function, and now it has the answer, right? And so we want to look at what's happening at layer 19 to figure out whether indeed there's some kind of abstract function that is being applied at this layer. We do find that this pattern of the argument peaking and then the answer peaking is generic. It happens across different models, and it happens across different tasks. So here I'm showing results on 2 different models. The top is Bloom, which is a large 175 billion multilingual model. The bottom one is GP2 medium, which is much smaller, on the order of millions of parameters, or maybe single digit billions, I forget, only on English. So they're very different models. And they also, and then the columns are 3 different tasks. I forgot to label them, and I keep meaning to. But one of these tasks is for a country retrieve its capital. One of them is for a verb retrieve its past tense, like for a present tense verb retrieve its past tense form. And one of them is for a lowercase word produce the uppercase version of it. And so in all of these cases, you can see that at basically the same layer for a given model, the argument first peaks in as the top choice, and then there's this crossing pattern where then the function gets applied and the answer becomes the top choice. And so this seems to be happening at a consistent spot. It seems to be associated with this particular layer in the model. And so we say, okay, that's kind of the working hypothesis, is that the feed forward net at layer 19 is applying this very specific function, right? And so what we want to ask is whether it's an abstract function, because it could just be that at this layer, the model has figured out enough stuff, and then it idiosyncratically has pulled in the answer Warsaw here, or the answer Paris here. So that would be kind of like there's this feed forward network, which is basically a Warsaw retriever. But what we hope is that it's more abstract. And in that, if it's more abstract, then it should transfer to some new context and always perform the function of retrieving a capital city for a country. So we can imagine.
Ellie, will you accept a clarification question from
Yes.
Stevenson?
Yes, definitely.
Okay,
Yeah, hi. Can you hear me?
Yes.
And see me? Good. Yeah, if you could go back to the slide where you were showing the delay. Yes, that one. Are all those models trained with the same amount of data?
No. So Bloom is trained.
That's interesting. So that's not really my question. I was clear. So I like this, but I'm wondering what happens. What's your theory of the flat kind of induction period here? What's that all about? And I'll just stop.
Yeah, that's a really good question, and I wish I had, if not a really good answer, like an answer. I will say, like, we're looking into it. I think so. There's I'll show, like, maybe in the last paper that we talk about, like something that can kind of give some insight into it, but like there's a lot of work that happens really early in the early layers, which is kind of lack of a better word, memory management, like figuring out what the task is. So there's like a lot of work happening in the attention heads to move stuff around and kind of get things in place that doesn't actually have an impact on the residual stream yet. So the model hasn't actually figured out enough of what's going on to have an idea of what word it wants to predict next, but it might be figuring out enough to know what it needs to do at this layer so that in a few layers it will know what word to predict next. So the kind of stuff you might see happening is like the model is, say, if we think about the register version of things, it's like collecting all the relevant nouns and storing them in a specific place so that a later attention head knows to read from that place and can do some particular thing. So there's this kind of like memory management stuff happening, but we don't have a really clean story of it. And we're trying to characterize them, but maybe the third talk or the third paper that I talk about will kind of start to hint at that a bit more. Yeah.
There's another question here from the room.
Sorry, can you hear me all right?
Yeah, I can hear you great.
This is pushing you a little further into the question that you're having problem answering. But I'm curious do you have an idea of how generalized that, grokking phase or putting things in order phase or memory management phase is? You were talking about collecting all the nouns in that. Are you seeing that's kind of, no matter whether we're predicting capitals or translating, are we kind of doing the same things with the registers and all that you're talking about?
Yeah, I think so. My hope is that it is fairly generalized. So the last paper that I'll talk about, and that's our newest one, what I got very excited about was just, we do find some evidence that there are there's specific steps that seem to be being used across otherwise very different tasks. So for example, there's for two tasks that both involve like duplicate tokens in very different things, there's like a particular thing that will find the duplicates, it'll set up some inhibition cycles, and it'll do these particular things to say, don't say this word again, or do say this word again, depending on the task. So in the last bit I talk about, that's where we have some evidence that there is actually shared components in this early phase, that it's not totally idiomatic. My concern before we worked on that paper was that the stuff that's happening down here is task by task, and so there's not really anything interesting and generalizable happening. But I think that the third paper I'll talk about, I think, does suggest that there's some interesting shared stuff happening here, and that makes me optimistic that maybe we'll find even more bigger shared structures.
Thanks.
For sure, yeah. That's a great question. Cool. So what we want to do here is we want to take this, pass this input through the model. What is the capital of Poland? We see it produces Warsaw. We're going to grab the piece that we think is responsible for applying the function, which, like I said, is just that O vector. So it's just a single vector that we're pulling out at this layer. And what we want to do is just splice it into the model at a different point where the model was going to say something else. So maybe we give it an arbitrary sequence of tokens where the next word it's about to predict is China. And if we just stick this in here, we're saying, well, if this is a general purpose like capital retriever, it should produce Beijing instead of China, even though there's nothing about this beep boop China beep boop that should suggest that Beijing is a good thing to produce here. And what we see in this particular, the Beijing case, is that's exactly what happens. It happens very cleanly, that the probability that before doing any intervention, the model was never going to say Beijing, because why would it? There's nothing about this context that suggests Beijing. But when we add in this feed-forward network, it produces Beijing. And what we should probably plot here is it doesn't produce Warsaw, right? So this intervention doesn't just make the model produce Warsaw, it makes the model produce the capital city of whatever's currently at the top of the residual stream. Right? And this also seems to generalize across models and tasks. So this is the one where we look at mapping capital cities or mapping countries to their capital cities. So we're looking for a gap between like the bluish lines and the greenish lines. And we also show it generalizes to state capitals as well. We have the same thing for lowercase to uppercase, which actually has the really strong effect. And then we have the same for the present to past tense verbs. I will say we have follow-up experiments that I didn't include slides. This really only works for these like one-to-one relations. It's a very specialized type of mechanism. So if we ask it to like retrieve the profession of a person, if you say like, what is the profession of Bradley Cooper? And he is an actor and a director and a, author and a public speaker or whatever other things are his possible professions. It'll do a very bad job, right? Like so this really only works for things like the kinds of relations I'm showing that are these one-to-one mappings. But within those one-to-one mappings, it seems to be a pretty stable finding. The second thing we look at, like I said, we kind of talk about this because this is the feed-forward network that's doing this. And so it's really working when it has to pull in this information from memory, say, and it's not always the case that you need to do that. So you could imagine something like what I've just been presenting is this, what we call the abstractive setting. We're basically asking what is the capital of China, and nothing in context tells you that China, that the answer is Beijing. You have to like remembered that from training. But you could also imagine a different setting where you just tell the model something like the capital of China is Beijing, and now you ask what is the capital of China. And in this case, the model should be able to succeed just by parsing language and pulling out the answer being Beijing. So what we want to see is whether this mechanism that we found with this feed-forward update is responsible for the model succeeding in both of these cases, or if it's specific. So what we're going to do is we're just going to delete it out. We're just going to prevent these feed-forward nets from firing. And in fact, we're actually going to do it at layer 19 and all of the subsequent layers because we find a lot of redundancy. I can elaborate if people are interested. And what we're looking at is just the accuracy. So if we just start ripping out these feed-forward networks, how much do we damage the model's performance? And so this orange line is showing the performance in the abstractive case. So this is the so this is the case where that we've been talking about, where you have to retrieve from memory. And you can see that once we remove even just the last feed-forward networks, performance tanks. Like you really need all of those feed-forward networks in place in order for the model to do this. But if we consider the extractive case, so if I say the capital of China is Beijing, what is the capital of China? Then actually just removing the feed-forward networks entirely doesn't seem to damage performance until I remove so many of them. So I should say going left to right, or I guess going right to left, you're kind of working backwards. So rightmost point is the full model. The point slightly before that is if I've removed just the top layer feed-forward net. One before that is removing like the top 2 layers or et cetera, going all the way back. So you can see that you can basically rip out the whole top half of the model feed forward nets and not hurt performance on the extractive case, which means that the attention mechanism is doing everything you need to do to succeed in the extractive case, but the feed forward network is really essential for that abstractive case. So summarizing this first paper, we're focusing on this very kind of simple piece of language processing, which is getting this factual information from memory. And the thing that's interesting is that this large transformer language models seem to have implemented this step in a, like, at least for these particular one-to-one relations, in this very simple, very compact mechanism, right? Just this little linear update at a specific point in the model. It's I was surprised by how modular it is. So you can move it to a new context in this zero-shot manner and kind of get the expected behavior in general. And it seems to only be invoked when the model needs to retrieve information from training, right? So it doesn't really apply when the model is can work with what it has from context. I kind of have these intermediate discussions, so I'll kind of go through, but then move on to. So like I said, this breaks down for one-to-one. There's more investigation needed there. And one of the big problems we're working on that kind of gets to those earlier questions is, how does the feed forward network know what to do here, right? Because feed forward network number 19 at token position 20 or whatever can't only serve as a capital city retriever. Sometimes it serves as a capital city retriever, but other times it serves as a uppercaser, and sometimes it's a past tensor, and sometimes it's going to be something else entirely, because most contexts don't require capital cities. So there's definitely work happening in those earlier, what I call the preparation or grokking phases, that are going to have to tell this feed forward network what to do. And we're trying to figure out kind of how do we trace back to those things. I have some preliminary results kind of in the last section of the talk, which start to point to what that might look like, although it doesn't really provide a full answer. There's another really interesting thing that I think is worth thinking about for connections to kind of the studies of cognition and reasoning and logic, which comes up a lot with cognitive science, linguistics, philosophy, as well as computer science, which is this distinction between what we've typically referred to in NLP as linguistic knowledge versus world knowledge. And this is, I worked a lot on entailment during my PhD. There's always kind of assumed to be this distinction, like me knowing that if Fido is a Daxi Blick, then Fido is a Blick. It like relies on my linguistic knowledge. It doesn't rely on just like my ability to parse the syntax of and semantics of English. Whereas knowing that the capital of China is Beijing, it has nothing to do with my linguistic knowledge and is world knowledge. We have this general intuition that there's a separation between those, but it's really hard to draw a clean line, and it's quite messy. And so this kind of distinction between the feed forward net and the attention mechanism feels like something that might be able to shed light on that, at least in language models and possibly more generally. So I think that's like a really interesting thing to pursue. All right. I can roll into the next talk, which kind of the next paper, which builds on this one, but maybe I'll take a brief pause in case there are other questions on this first. All right.
That's okay.
Cool. Cool. So this next study, so this one, so again, my student Jack and Shinan, one of the undergraduates here who's been working with us since she was a freshman, is doing really cool stuff. So here they wanted to follow up on this issue of kind of the retrieving information from memory versus working with what you have in context. So we had this, distinction between an extractive type of setting where you tell the model what is the capital of China versus an abstractive where you just ask the model and it needs to conjure up an answer. And we just described why these seem to rely on different mechanisms. So the question is, what happens if they compete with each other? Like, how does the model decide which one to use? So you could tell the model in context, the capital of China is Warsaw. What is the capital of China? And now the model needs to decide whether to say Warsaw, relying on its kind of linguistic reasoning attention mechanism, or whether to say Beijing, the thing it knows to be true from training. So that's how we're going to set up the task, is we're always going to give the model this, this prompt that says, that asserts the capital of a country to be different than what it actually is, and then asks what's the capital of the country. We'll call this the country. Here, London is the in context answer. That's the thing that the context is telling you is correct. And then Warsaw is the memorized answer. That's the thing that your training data should tell you is correct. And I should say for all the models we work with here, if you just ask what is the capital of Poland with no, like just that question without the preceding sentence, they're at 100%. So they do know the memorized answers, right? So we're trying to ask whether the model will say London versus Warsaw and what dictates that decision. So the first thing we looked at was just the role of frequency in the data at the model's decision to prefer one answer to the other. So we looked at a lot of different measures in frequency. Here it's literally just the count of the country. So this is just how common is, or how frequent is the word Warsaw in the training data. We looked at other things like mutual information between Warsaw and Poland, mutual information between London and England, mutual information between London and Poland, like all kinds of other metrics, and they all show a very similar pattern to the ones I'm showing here. So what we basically see is as the frequency increases, the more frequent the thing is, the more likely the model is to produce the memorized answer. The otherwise fall back on the in context one. This is fairly intuitive that you would say, well, maybe if the model's encountered this fact more times, it's just much more confident in it. Otherwise, it's more likely to use this in context answer. It's also a thing where we see a strong interaction with model size. So here we're looking at a suite of models called the Pythia models. These are open source models that are like identical except for size. So they've been trained on the same data, but they're different size models. And you can see that at the far left, the smallest model, there's actually a just overall preference to produce the in context answer regardless, and very rarely does it produce the memorized answer. Whereas when we look at our largest model, the one that's about 3 billion parameters, it very much prefers the memorized answer, but it's not as though the whole thing, the change isn't linear. So as the models get bigger, they prefer the memorized answer more for the most frequent countries, and then only as they get bigger and bigger does that tail come up. So we do see this strong frequency effect. But the second thing we want to look for is like a mechanistic effect. So what is actually, determining whether the model produces one versus the other, and is it possible to force a model to produce one answer versus the other? So here we're going to use a technique called path patching. This has been introduced in pieces and parts over a couple papers. I'm citing the Wang et al. Paper, which recently, because we stole their figure for this, but the original idea came out, I think, in Vig et al. Is like called causal mediation analysis. So there's like a number of papers that have proposed this kind of method. There's a lot of weeds, but the basic idea is we're going to look at the attention mechanism, and we're going to break it down so that for a single attention block, we can get word by word updates. So we can say how much is a particular piece of the attention, or what we call a head, contributing to the probability of London in the residual stream versus Warsaw. So we can say like this head, and we're going to contrast in this minimal pair setting. So we're just interested in London versus Warsaw in the residual stream. And we're going to say for a particular attention head, is it basically pushing in the direction of London or pushing in the direction of Warsaw? And the more it's pushing towards London and away from Warsaw, the kind of darker here. So here, I would say the darker red, the square is, then we're saying that's a particular attention head that's really promoting Warsaw over London. If it's dark blue, we would say it's really promoting London over Warsaw. So this is kind of a semi-quantitative way of identifying particular attention heads. So these are a small number of parameters within the network, within the attention, that seem to be playing an outsized role in what the model predicts. And so here we're going to identify, we're going to be just really conservative in our analysis. So we're going to pick a single head. That's the one I have circled here, which we say is the one that's most responsible for promoting Warsaw. We're going to call this the memorization head. And then there's also, I guess, this dark blue one that's up here at layer 7, where we're saying that's the in context head. So that's the one that seems most responsible for wanting to promote London. And what we want to do is we want to ask whether this head itself is basically serving as like the router or the decision point that tells the model to produce the memorized versus the in-context answer. So what we look at is the figure here. So we're starting by saying, let's just look at this memory head, that we found. And in its default setting, that's what these dots are showing. So when we have a kind of a ratio or a multiplier of 1 on it, so just as it is in the model by default, we see that 100% of the time the model is predicting the memorized answer, and basically 0% of the time is it predicting the in-context answer. And then what we're going to do is we're just going to multiply this head, the update this head makes by a scalar. So we can either kind of turn it up or turn it down like a knob. And we're going to see how that affects the model's tendency to predict one versus the other. And you can see in this case, you get a really strong effect. So actually, if we just turn this knob down, we can make it so that the model almost always predicts the in-context answer, right? Which is a pretty dramatic result, where we can see that we kind of turn off its tendency to listen to its training data and turn up its tendency to listen to what we just told it in context, just by changing this really very tiny number of parameters, just this single attention head, which is like on the order of, I forget, but like much less than 1% of the whole model, right? This is just showing for that memory head, which is where we saw the cleanest results. We play around with the other heads so we can look at the effect that they have, that the different heads have, and we can also look at it at different slices of the data, and we can see that the patterns aren't always as strong as that first one I showed you, but they consistently move in the right direction, where we can see that tuning the head leads to a decrease in one and an increase in the other in the way that we're expecting, although rarely, only in that first case were we able to get the like full swapping of behavior. So there's kind of interesting finding here, where the first that we see that the preference for the in-context versus memorized is at least in part dependent on model size and training data. But there's these specific attention heads that appear to mediate whether to use one piece of or one type of memory information versus the other. And that we can have these types of interventions that can affect whether the model makes one type of decision versus another. But it is interesting that the results are asymmetric. So in this case, it was easier to make the model prefer the in-context than to make it prefer the memorized answer. This possibly has implications if you're into like practical implications. Like one thing we thought about for why we might care about this in practice is like to make models resistant to what's called prompt injection. So like if people try to hijack a model to get it to do bad things, you might want to make it less sensitive to in-context information, but that actually proves to be the harder direction. So there's possibly some bigger implications there that we haven't gotten the time to fully think through yet. Okay. So that kind of wraps up what I wanted to say about this general like memory retrieval piece, which is, I think, more about the first about the feed-forward nets, the second about the intention and its connection to the feed-forward nets. I'm going to switch gears in this third paper to talk about finding these more general circuits that ideally generalize across tasks. But again, I think I'll pause for a second in case there are questions on it.
Quick question, Ellie, again.
Yeah.
It's Steve Hansen. So the really dramatic change from one output to the other that you'd shown by continuously changing one variable. What was that variable you were continuously changing?
Yeah, so it's the output of a single attention head. So when the attention, yeah.
And is that and you just did a linear increase in it, right?
Yeah, we're like literally just multiplying it by a scalar.
So this is also probably for Stephen. So that's actually a categorical perception effect. I'm not sure you know that, you might. And this is Stephen published a book on CP
Cool.
before this, and you're actually showing really strong CP effects.
That's very cool. I will write that down. That's something I should I'll look at your book, Steve. That's really cool. Thank you.
Yeah, okay, go ahead.
I have a general question.
Yeah. Yeah.
Yes, hi. This is a general knowledge question. When we talk about the size of the model, does this include also what's in the registers or only the weights of the network connection?
It's the number of parameters.
Only.
So
Okay.
it's just the weights. Yes. Yeah.
Okay, thanks.
Because I think, yeah, I would say the rest doesn't change across models, like the size of the activations.
Okay, yes, because I was confused by the registers issue. I thought like they also memorize and contain some memory that is saved for yes.
Yeah.
So,
Right. No. Yeah, like the registers are
dynamic, like,
defined by the input. They're dynamic. Yeah.
Okay,
oh,
for just a sec, for organization reasons, wait until I recognize you to ask questions, otherwise it's going to become a chaos. Okay, just raise your hand on the screen and I'll recognize you, but don't just jump in. There is because I have to coordinate it with the people in the class. Go ahead.
All right, so
Identify yourself.
my name is Dennis Drown. My question is actually partially answered on the one before, that first one from the series. Where you're tuning the weights on these attention heads, you said that you're tuning the output, the weights going out of the actual neuron or head. Have you looked at this with tuning the inputs, increasing or decreasing the input weights? Is there any difference or?
I don't think we looked at that. We looked at a couple different things, but I forget exactly what. So that's a really good question. We should play with it. Like I said, this is a kind of we kind of did the simplest thing here, and I think there's probably more sophisticated things because yeah, like obviously there's going to be I guess upstream determinants of this behavior. So yeah, possibly an edit further upstream could lead to different effects. Yeah. So I'm not sure. I don't think we looked at that, but that's a really good point. Yeah, thanks. Awesome. Okay, great. So I wanted to finish with kind of our most recent work in this series. So this was work that we just wrapped up like last week on looking for kind of more general, what we call circuits. So multiple steps of these attention heads and things working together to perform a more general task. So here we're building very directly on this work from Wang et al. That we're looking for circuits in the context of a particular in a particular task. So in their task, the red task, they were looking at this language modeling problem where you say, then Matthew and Robert had a lot of fun at the school. Robert gave the ring to blank, and here we're expecting it to predict Matthew. They call this indirect object identification. And then we're looking at the circuit they find for that, which I'll describe. And then we want to see whether it generalizes to this different task from Ippolito and Callis and Birch, which is just kind of a simple linguistic reasoning task, or maybe even syntactic processing task. So it's on the table, there is a blue pencil, black necklace, yellow lighter. What color is the pencil? And the model is supposed to say blue here. So most of the findings that we're showing are the consequence of using this path patching framework. So we're going to keep using the same method that I just described for finding those attention heads. And basically the way you proceed to find this whole circuit is you work backwards. So you start at the top of the model and you say what heads were most responsible for predicting the correct answer here, as opposed to some alternative. And then you work backwards and say, well, what attention heads were most responsible for the behavior of the head we just found? And then for those heads, and you say what affected those and in what way did they affect them? So it's kind of this top to bottom search over what is the circuit of attention heads and what exactly are they telling each other in order to carry out the task. And this can give us kind of insight into the like algorithm the model is running. So like I said, we're going to build really heavily off of this previous work from Kevin Wang et al. And they were looking at finding a circuit for this particular task, this indirect object identification. So I'll first describe what they found in their paper. And then our question was, okay, this is cool. We find these circuits. If we find these circuits, does that mean that we've learned something general about like how transformers are thinking about tasks? Or are we going to have to find a new, is every circuit going to be very task specific and idiosyncratic? And so, yes, we can find a circuit for a given task, but then it won't generalize to new task. And so what we're interested in is whether the circuit we find here will generalize to a new task. Okay, so I'm first going to describe the circuit they found, and I'll start by kind of working backwards because that's how the path patching proceeds. So I think it's easier to understand that way. So if you look at the kind of top level, at the very end, right when the model predicts Matthew, they find that there's an attention head, which they call the name mover head, which basically the thing that that head appears to be doing is copying names from the previous layer into the residual stream, right? So if we think of them as reading and writing, it's reading from anything that contains a name and it's writing to the current spot, right? And then in parallel to that is something called this negative name mover head, which basically does the same thing, but it actually demotes, it tries to prevent this writing from happening. They reason that this negative name mover head is kind of serving as a hedge against the name mover head, but you just see these heads that seem to be specific to reading names and writing them to the current spot, right? So then when you say, well, what informs these name mover heads, if you work backwards, they find this head a little further upstream that's called they call the subject inhibition head. And what it effectively does is it tells the name mover head, it prevents the name mover head from attending to Robert in this case. So it says, okay, I know what you're going to do is you're just going to copy all the names that you see. So I'm going to block you from copying Robert so that you copy the remaining names that I haven't blocked. Right. And then if you go further back and say, well, what tells that subject inhibition head what to block? There's these earlier heads that are, they're basically duplicate token detection. So they find that the name Robert is repeated. They tell the subject inhibition head, block the repeated name, and then the name mover heads go ahead and do their name moving thing on the remaining names that haven't been blocked. So to kind of play the algorithm forward, which is maybe an easier way to think about algorithms, the model first in these early layers identifies duplicated names. Then it alerts the subject inhibition head of the location of the duplicated names. Then the subject inhibition head kind of sets a blocking signal over these registers that makes them, that prevents later things from attending to them. And then the name mover head moves the names that it attends to, but it's been blocked from attending to the duplicates. And so it puts Matthew in the correct spot. So that's the kind of general circuit that they describe for doing this specific task. So now our question is, okay, now let's look at a different task. We have this colored objects task. And here we're going to use a one in context learning example case, just because the model doesn't do very well. I mean, it still doesn't even do very well, and I'll get to that later. But so you ask it to identify the color of objects from a set of example or from a list of objects, and fill in the blank here. And so we have, this is the circuit that was found for doing indirect object identification. And you can see that there's kind of on some level, there are similarities between this task and the indirect object identification task, because both tasks require some kind of syntactic processing. They require some parsing. They deal with recognizing repeated tokens. But on a kind of linguistic analysis level, they're very different. Like if I had to use the Stanford Core NLP pipeline to write a solution for the colored object task, it would have very few steps in common with the indirect object identification task. Like they're going to use different parts of the parse tree or whatever. So we're going to now do the same thing that we just said. We're going to work backwards and say, what is the circuit for identifying or for solving the colored objects task? So the first thing we do is we find that the name mover head, the exact same head that was doing name moving in the previous task, the IOI task, is now copying colors. So it was attending to names, now it's attending to colors, and copies them into the residual stream. We don't see a negative name mover head at this point. I'll come back to that. Then when we go backwards, we don't see this subject inhibition head, but instead we see what we'll call content gatherer heads. We borrow that name from a previous work that coined that term for a different circuit they were looking at. But what these content gatherers do is they focus the attention of the name mover head. So they're basically telling the name mover head that like you should attend to these colors, right? Rather than blocking attention. And then prior to that, we see the exact same duplicate token heads are informing these content gatherer heads. So they basically tell the content gatherer heads, you should pay attention to the duplicated word here, and you should route attention to the color preceding the duplicated. So we see a very so I should just say, to play that algorithm forward for the colored object circuit, first we have this same duplicate word detection, and this is using the exact same attention heads that were used in IOI. Then it informs the content gatherer heads of the locations of the duplicates. The duplicate sets like a flag that says these are the things that deserve the most attention. And then the name mover heads attend to the colors associated with the duplicates, and copy as they usually do. So we see this interesting picture where actually of these two circuits, we have kind of two pieces of it that are identical. The name mover heads are, which I guess now should maybe just be called mover heads, are doing the same thing in both tasks, and the duplicate token detection is doing the same thing in both tasks. And then we have some differences where the colored objects task is using this content gatherers, whereas the IOI is using this inhibition, subject inhibition cycle. But it's very worth pointing out that the model, and here we're looking at GPT-2 large, is perfect at IOI. It gets 100% accuracy, and it's quite bad at colored objects. It's actually a little bit better than chance, but not much. So it's at about 50% accuracy, and and chance, if it chose randomly between the colors listed in the prompt, it should be at 33%. And actually what we see is what it is often doing is it's randomly guessing between the colors. So it's not producing garbage, but it's, in this example, it would be randomly guessing between blue, black, and yellow. So a little bit better than chance, but not much. And so the question is, well, there's a lot of overlap in these circuits, but there's these pieces that were active in the IOI circuit that don't appear to be active in the colored object circuit. And it actually seems like inhibition is really what's necessary and missing here, because the model is saying something like black and yellow, and that seems like exactly the role where the inhibition heads were supposed to tell the model not to say black or yellow, right? So we look at what is happening to those two inhibition heads when we run it through colored objects, and we find two things. So the first thing is that for the subject inhibition head, we actually find that it is active. Like when you look at what it's reading from and writing to, it's doing the same thing it does in IOI. It's actually placing inhibition signals on all of the color words, and also on the previous example to the answer orange here. But the problem is that it's a very weak signal, and it doesn't seem to be appropriately biased towards the wrong answers. It's also placing a lot of inhibition on the word blue here. And then if we look at the negative name mover head, which is also supposed to have this effect of basically demoting noisy, or demoting kind of and hedging against accidentally producing the wrong answers, it's actually active. It's doing the thing of demoting what it attends to, but it's just sitting on the first token of the sequence. And anecdotally, what this tends to mean when attention heads are just looking at the first sequence, or the first or the last token of the sequence, this is kind of what I like to think of as benched. It's basically the model saying, I don't know, like, you don't have any role to play right now, so why don't you just hang out here until you're needed? And so they're just kind of hanging out there. It's doing what it's supposed to do, which is saying, don't produce Q as the next word prediction, but the model is not going to produce Q anyway. So it's just kind of hanging out there, going unused. So what we want to do is say, well, what if we just reroute the attention of these heads to kind of intervene and patch the circuit a bit, to say, like, we know you have these inhibition components. They worked very well in IOI. They should work well here. If we just point their attention to the correct places, will that have the correct downstream effects and improve performance? And it very much does. So here you can see that on the more relevant figure is on the right, where we can see that by intervening, we reduce the downstream attention of the mover heads to the incorrect answers. And what we end up with is an almost perfect recovery of the accuracy in this colored objects task. So that we go from, a little bit above chance to 95% accuracy, I believe. So the kind of finding here, I think one of the big important findings is that there's these individual circuit components that are actually generic and reused across tasks. So those mover heads and those duplicate token detection heads, for example, the exact same heads were performing basically the exact same role, but as a step of two different types of algorithms used for solving these two different tasks. And kind of knowing about this and knowing about the types of components that exist and are used gives us some insight into these kind of building blocks that the transformers are using. So like when we think about traditionally how we would think about a language processing task, we kind of have these algorithmic building blocks. Again, I think of something like a traditional NLP pipeline where you'd have these part of speech tagger, you'd have your parser, and these are like the things that get computed and recombined in different ways to do different linguistic reasoning tasks. And when we look into a transformer, we can see the kind of early signs of similar building blocks, which are not the same ones, but they have the same benefit of telling us like what are the fundamental core components and modules that are going to get mixed and matched. And when a transformer is approaching a new problem, like it's going to try to break it down into the terms it understands. And these seem to be the kinds of terms it understands, right? And they may or may not have a good connection to what we think about in language processing in humans. And we can kind of show as a proof of concept that knowing about these two different circuits, we can mend broken circuits and have substantial effects on performance. And we have some kind of hypotheses about why we needed to manually mend it in this case, which I'll talk about later. But it does give us this kind of insight that like these components actually do work in a generalizable way such that we can like invoke them in a new context where they weren't being used, and then they will act the way they're supposed to, and they will have the desired effects. So the kind of things we're thinking about right now is like in this colored objects task, for example, we had to like go in and reroute the attention. It was a small intervention, but an aggressive one, right? And so it's something we would like to figure out why the model didn't know to do this on its own, right? We have some different theories. One of them really gets at the thing I was talking about at the beginning of the talk, which is that this computation has to take place over the layers of the model of the transformer. And these different circuits exist at specific spots within the transformer. And so if you kind of trace how long it takes the model to figure out the task, there's this risk that you can kind of miss your window and have lost your opportunity to access that circuit. So if I'm a transformer, I'm dealing with the colored objects task, it takes me until layer 17 to realize that there's a need for inhibition here, but all my inhibition heads I left behind at layer 14, SOL, right? There's not much that the model can do because it just lost its opportunity to use those. So this is a place where you might imagine adding some recurrence into the architecture might actually help. It'll allow the model to take longer to figure out a more complicated task, but then still make use of its existing components. So that's something we've been thinking about a lot, is first trying to show that that is in fact possibly the source of the problem, and that adding some recurrence should help. I will say that has been other work, I think Morgiva, this was also from her group, that suggests that transformers kind of have this homegrown, half-baked recurrence where they basically introduce a lot of redundancy across layers. And we saw this in that first paper with the capital city vectors. So they'll reproduce like identical mechanisms at many, many consecutive layers. And that might be their kind of hack for getting around this problem, right? So that if it takes plus or minus several layers to figure out the task, you won't have lost your chance to use a particular mechanism. The Morgiva paper showed this by showing that you could actually just reorder layers like wholesale within the transformer without a effect on performance. You could just say randomly shuffle layers, 13 through 17, and the model will still perform fine, which is, shocking to me and says a lot about this kind of redundancy that exists. If you randomly shuffle all the layers in the network, you completely break its ability to work because those early layers kind of contain fundamentally different mechanisms than this middle and late layers. But there's a lot of redundancy within the middle and late layers. So we might be seeing something like that happening here, and it could explain why the model failed to invoke its own inhibition circuitry, right? The other issue is that, or another kind of hypothesis, possibly related, is that the model is just not sufficiently trained. We're dealing with GPT large, which is by today's standards, a small model. By 3 years ago standards was huge. But it's still, by today's standards, a fairly small model. And the colored objects task is a more complicated task than the IOI task. It's a little bit more distant from traditional language modeling. And so it might be that for the model to figure out that task, it needs to have just trained more. And we have a lot of evidence from other work that building circuits happens slowly over training. And so the model might be exploiting heuristics as it's in the process of building these circuits. And then after sufficient training, so like you might see train loss plateau, dev loss plateau for a while before the circuit is fully formed. And then all of a sudden you get a sudden drop in the dev loss. And that's what we might be seeing happen here, is that we have this circuit, the model started to form this colored object circuit, but it didn't fully figure it out before we stopped it from training or it maxed out. And so maybe we can track how these circuits are evolving over training and get more insight into what might be happening here. All right, so I'll kind of zoom back out. So kind of the meta discussion over all of these papers, I think of one of the big things I've just been really obsessed with the past couple of years, and that's been a big change for me since, you know, what I used to work on during my PhD, is just not making this assumption that these neural networks are inscrutable black boxes. Actually, a lot of the architecture of transformers specifically seems to call to mind these kind of specific computational ideas from symbolic machines. But it's also not all about what's innate within the transformer. That's a fascinating piece of it, and it definitely seems to be a piece of it. But a lot of the mechanisms are emergent. So the specific heads, this inhibition heads or mover heads, or this feed forward network applying a specific function, that's not an innate inductive bias of the transformer, but it's something that the transformer develops during training. But once those things are there, like once these emergent components are there, they basically function as though they were hardwired in, right? Like wiring is wiring. And so we actually find that they're reused in different ways. They can impart inductive biases on the model. They can be task independent. They can generalize. They're surprisingly modular and even interpretable to us. So something I'm very excited about that I think over the next couple of years we'll hopefully see happen is just the potential of language models to actually yield some fairly specific theories about what kinds of representations and mechanisms are sufficient for explaining kind of these higher level cognitive things like language and reasoning and other kinds of abstraction. I think that right now there's often this kind of very straw man argument that is made that is like, because the language model succeeded, you know, everything we thought we knew about language is wrong, which is both probably not true and also not particularly helpful because it doesn't tell us what is right. And the language model itself doesn't propose a theory or mechanism. But if we can pick apart what is the algorithm it's running, what are the data structures it's using, how are they relating to each other, we get this really exciting time of being able to generate some of these new theories that then we can go test in humans, and it can kind of bring the whole study of language and cognition forward in a way that feels much more tangible. So with that, I'll say thank you, and I'm happy to take whatever questions.
That was terrific. I want to thank you. It was the difference between your talk and the ones that came before it is that the other ones took for granted or the success of GPTs, LLMs, and then interpreted it from the point of view of their disciplines. You have not taken anything for granted. And you're not even satisfied with that, you know, how LLMs are working yet, and you're taking them apart. And that's exactly what was needed now. So I want to thank you for that. I have a few icebreaker questions, but anybody, if you have, we've got less time than we thought we would have. If you've got a question, raise your hand right away and I'll recognize you right away. Yeah, okay, go ahead.
All right, Dennis Drown again. This is in regard to the suppression headers. And you kind of partially answered along the talk on the third part. But my initial question was, are they, because just from the name, you would think that they're not activating. It's like a negative signal, but I think probably they are. You have an active signal, it's something that's gone ahead and, you know, hit its threshold and is sending out a signal to the next layer. And then that is then going to suppress the subject or whatever it's doing. So the question kind of turned into, well, assuming that is true, you can tell me if that's not true. Are there these kind of negative, like maybe headers that are normally on in a general sense, and then when they turn off and don't activate, you see some kind of changes in the rest of the circuit the way you're talking about? Does that make sense?
Yeah.
Ellie, could
Yeah.
you turn off your PPT share?
Oh, yeah.
Okay, go ahead.
Yeah. So let me try to answer and you can tell me if I missed it. So yeah, I think there's kind of two ways that there's kind of two mechanisms for inhibiting. There's like this negative mover thing, which is basically saying, attend to me. Like the register says, if you attend to me, I'm going to tell you not to anti-copy me, right? So if I contain the word cat, you should demote the probability of cat. That's the negative mover signal. And then there's another kind of inhibition signal that basically says, don't attend to me. So these can just be different. Like there's this, you can break down into the transformer has this weird attention mechanism with keys and queries and values. And so it can splice up different ways that it can influence downstream computations. So there's slight differences in how you might inhibit. And I think in these two tasks, the circuits are quite short, right? They're really like 3 stages. It's like detect the duplicate, inhibit, copy, or detect the duplicate, promote, copy. So it would be really exciting to find a larger circuit where that inhibition has to engage in some longer, non-trivial feedback. And in particular, if you could find something where like inhibiting the signal causes a whole different circuit to fire or something like that. So like you might imagine like, well, it's not quite the same thing, but like in this content, the colored objects thing, we were saying, well, the S inhibition head doesn't fire also possibly because those tokens are not duplicated. So we want to duplicate we want to inhibit the word yellow, but yellow is not a duplicate. Maybe that thing only fires for duplicates. There's like these interacting components. So I think we probably need to just find more complicated tasks where you would see like a more interesting circuit. I think we've been talking to neuroscience and like looking to neuroscience because there's a lot of good examples there where you need these negative feedback loops for like larger circuits. So I think that's a really interesting line of inquiry. I don't think we have a good answer. And part of it is like the circuits we're looking at are just so short that it's hard to see the kind of thing that I think you're asking about. I'm not sure if I misunderstood the question.
I think actually that answers another question that's also very similar, but it's still an active negative signal. Like it's something that's activating and then propagating. I guess another way to ask what I was meaning to ask was on the heat maps, the dark colors are where that particular module is activating, right? Have you noticed anything interesting where ones that maybe are kind of a pale color are white all of a sudden? They're not activating. Is that creating some kind of effect?
Yeah, I think. Yeah, if they're just not activating at all. I don't think I have a good answer for that. I'd have to follow up. Yeah. Yeah, I don't think I have a good answer.
All right.
There's a lot to dig into in those. Yeah.
Okay, over to New Jersey.
Yeah, thanks, Stephen. I actually agree with Stephen on this talk. This was really an amazing talk. And frankly, it should be a neuro-IPS talk, a plenary talk at some point. There's a bunch of stuff in here to like. The Lashley kind of ablation study you did is really quite interesting because you're getting a disassociation. But I don't want to focus on that. I think you've got a tiger by the tail here, and you're good. And we're trying to do similar things that have been for quite a while to look at visualization in this. One of the things that strikes me in terms of your program is it reminds me of what Steve Pinker said back in 1990 to me. You'll never, ever find rules inside of these things. They can't exist. Okay, so you're kind of disproving this in the large. That's one aspect of it that kind of is exciting. But it also seems like there's a larger, like the lead of the story is being missed here. One of the things that has captured people's attention is the fluid, probably context-free grammar that this thing learns. And I don't understand this, and I haven't since 2017 when I talked to the Google Brain people who are doing BERT, And I said, so do you have a linguist working with you? No. I said, well, are you doing nouns and verbs? He says, what are those? Okay, so this is a real problem, as you pointed out, that there's a kind of a deep distrust of linguistics that obviously the chatbots have grown like a tumor and metastasized inside of them structure. But how?
Yeah.
And that's it. Now, the only thing I have that might be relevant to your story here is that I've been dealing with people at OpenAI, and the clustering space, there's a couple clustering spaces out there that have to do with the predicted words. And I think ChatGPT-3 had something between 100 to 150 million clustered context. So this might serve as a substrate in the way that your circuits are moving around, but more in a Roger Shepard geometric sense than in a rule-based Pinker sense. So I'll stop there. That's not a question, I suppose, but it's like, do you have any idea how it has this fluid kind of intellect?
No. Yeah, so the short answer is no, but I completely share your interest. I think this is fascinating. So like I think I've gotten into this work. So when I was like, the first stuff I was doing straight out of PhD was this kind of early probing stuff. So yeah, 2018, like right after BERT came out, and we did a lot of like, does it know basic things about syntax and semantics? Like, does it represent part of speech? So it's like, yeah, the transformer and everything about these models was, if not a distrust of linguists, just like a lack of patience for them, right? So it's like, we want to train the things fast. We want to parallelize, screw everything we know about language. Let's focus on building machine translation. And then it was good. And so then people were like, well, did it do this? Like, does this mean that those constructs aren't useful, or does it? But then what a lot of us were asking is like, maybe it actually just learned those constructs. So it's only succeeding because it had to figure that stuff out. Like, we could have told it that, but it figured it out, and it figured it out and then succeeds. And so that early work was like, yeah, it does seem to have figured it out. But the thing is, it's like, what I can't tell is like, did it figure out exactly what we would have built in, or did it figure out a slightly different flavor? That's actually going to be interesting. So a lot of this, as we've gotten more and more into the weeds, is trying to figure out like, yeah, what is the grammar that it has? Because it's not going to look exactly like the whatever Chomsky grammar we would have built in. Right. But it's not no grammar. It's definitely not no grammar. And if we figured out what it is, that's like a really exciting finding. But I don't think we have an answer for that yet. Right.
Good. I'm glad to hear the word yet. So the structure of this thing, of course, is the key to it. I think a lot of people have had, which I think is the cartoon connectionist versus the connectionists. I can speak for some of them. We're not thinking this back in the 1980s and 90s. We were thinking structure, but we couldn't find any. And the structure we did find seemed too trivial. That's partly because the task was too trivial. This has a disconnect, though, between predicting the next word from a large matrix of literally associations out of these attention structures that are, learned through gradient set, but they're still just associative at that level. But maybe they're second or third order, the way Sinowski talks about this. And yes, there's some neuroscience in this. I'm sitting in the Rutgers Brain Imaging Center, which I direct, and this is exactly the kind of stuff we look for in terms of hierarchical structure in the brain. But I'll stop here, and maybe we can take this offline sometime, because I'd really love to talk to you, Mark. And I'll let other people go in.
Okay, Pierre, it's to you. But you have very little time, right? So make the question short so you can get an answer.
I'll try to make it short, yes. Maybe, in fact, it's exactly the same question, but in a different format. In your example of Matthew and Robert, you use words like name and subject, but to me, you use them as linguistic attributes, not as LLMs are supposed to use the words. Now, does your LLM know about name and subject, or how do they get that?
Right. Yeah, no, that's That's a really good point. So yeah, I think, so I'll comment on subject first. So we call it subject because that's what that prior work called it. But actually they dug in a bit more, and it does seem to be quite position dependent, or at least like they were looking at that very narrow task, right? So all of their sentences had exactly that format. So you couldn't really tell whether this was a subject identifier or a token number 3 identifier. Like that kind of a thing. So it definitely subject is a liberal, being applied quite liberally here. In their particular task, it was attending to the subject, but it does seem to be quite focused on position rather than kind of syntactic role. And I think we were surprised that we could like use that same head to inhibit other things, but of course, like whether it triggers, it might not be so yeah, I think it's definitely not, it's too soon to say that it's doing something at all syntactic. Similarly, the names, I think we were probably should, and maybe we even did in the paper, switch to just calling them mover heads, not name mover heads, because they do seem to have this general, they're copying function. They're just whatever they attend to, they're copying. And something upstream tells it attend to me. So they don't seem to be name specific. But I don't think that in any case, whatever upstream signal is being sent, it's hard to say whether it knows what names are, what colors are, but like, I guess, Stephen was just saying maybe like there's like these various clusters, like they definitely have kind of concept categories that might trigger them. But somebody had asked in a week ago or something about this, and they were like, would the name mover trigger for any other capitalized words or something? And we didn't look at that, but I would imagine it might have these kinds of heuristic effects. So yeah, it's probably a bit generous to be using words like subject and name mover when really they're playing a fairly specific role.
Okay, and on the color example, you know that blue, orange, yellow are colors, but in the context that you gave, you just use the words blue, yellow, and orange. And in the questions, you use color. You can make the link, and it's not surprising that the LLM has more difficulties to make the link if the word color is not used in the context.
Right. So I actually did experiment a bit with that. So the what we call the content gatherer head, which is the one that's responsible for saying, hey, pay attention to the colors. That one itself reads heavily from the word color. So we did play around with saying that it doesn't get to look at that word color. And it did have a small effect on performance. Not as large as we wanted, but we think we might need to just make the intervention further upstream. And then I think there's just a strong heuristic on recognizing the duplicate of the word pencil that drives here. But one thing we plan to manipulate, it did seem that there was a circuitry that said the word color should influence what you attend to here. So I think if we manipulate the task a bit, so we say something like location, other types of things, we might be able to see downstream circuitry change, which would be really exciting. So I think there actually is something non-trivial happening there, not entirely heuristic, but I think in this case, we couldn't quite tease it apart.
Okay, maybe the something strange happening is some grounding of some of the symbols.
Maybe I can say yes because we're now at time and I won't have to defend the
Thank you very much for a very nice presentation.
Thank you very much.
I can only repeat that. It was terrific. Valerie, you have your face illuminated. Does that mean that you wanted to ask a question? Speak now or forever hold your peace.
No, I don't have a question, but I listened carefully. This amazing presentation. Thank you so much. I just opened my camera because I think it's that's the way it should be. Yes, you should see the people.
I appreciate it.
Listen to you. Thank you.
Thank you.
And please, Ellie, come back for some of these others when the others are talking. Keep them honest on how rather than just wow.
Okay, that sounds great. Yeah, it looks like a really great list of talks. So, all right. Thank you so much. Bye.